Okay, so this week we're gonna go Unit 2 and we're gonna take a look at the structure of materials. So we have about 110 chemicals. Some people call them chemicals, but scientifically we call them elements found in nature. Some of the chemicals, not all of them, you can create in the lab. For example, we can make like jewels, okay? We can make imitation gold, silver. We can also make sapphire, okay? Things like that. We can also make imitation diamond. So they all anyway by studying the structure of some of the elements, and we can create them back in the lab. It's just all about structure, and I've taught you since the beginning how important it is. The structure is the structure. A particular structure will give you functions and properties, and if you change the structure, these functions and properties can change. Okay, but then that is limited as far as what we know so far. Okay, and there are many things, phenomena that we don't know, not yet found or discovered, and we couldn't be able to get to that level, either going smaller and smaller or going bigger and bigger at that level of understanding. We don't have it. So maybe you have like a big stuff there, and we're living right here. Living mean knowing. Okay, you have brain and you have life and you have your body system and your generated mind, and you use your generated mind and study so many things, right, from time to time. Activities all the time, okay, activities happening from a point of space to a next point of space, we call that time. So if you look at human civilization starting and then now current right now, okay, today, and everything we have ever discovered is limited to our uh, structure, which is our body system. Okay, and of course we are very similar to each other, also individual. So the way that we think also different. The way that we understand also different. So the knowledge that we know about whatever we understand about the whole thing and components of the whole thing after this now are accumulative knowledge. Okay, cumulative knowledge. Okay, I'm gonna go ahead and erase this. So anyway, right now understand that so far we have found 110 chemicals or elements. Some people love to call it chemicals, and I don't like it. You have to go with everything we've got, okay? And we sort them out. So if you go outside and you take a look at your ground, and then you're gonna see some sand, rocks, right? If you dig, then you might find oil, or you find some metal ore, or things like that, calcium. If you go into the tunnel, let me start this thing here. Okay, and so everything that you see outside, everything you have inside of your home, okay, wherever you live, and are all made of, okay, mix mixed mixture of these elements. Okay, not all of them, just we mix some of them and then we use them. And some other we find them naturally. Okay, we don't even do anything about it. Okay, and never ever forget about the living things. Living things, you and I included, animals, plants are living things. So if you think about the wood, don't think like that just element and like that just material and it's not living. actually wood is connected to trees. Okay, trees are living; they are very living, pretty much, but they have again different structure. Yeah. So, but then in, after tree life, then we use them as wood. Okay, so you might see like wood has nothing to do with living, but then the cell structure in the molecules in their fibers in there are also built with some of the elements here. Yeah. So we've got to go inside internal structure and understand from the very, very basic one, so you know like how these properties build up and give you all the strength and more properties that we can be able to see and perceive at this level of life. So going down again to all industrial materials, they're composed of one or more, okay, of these elements out of this 110. So how are they making the structure? So if you think about at world level, right, at our human level, every time you want to make structure, you have parts, and then you're going to attach one part to another with something. Yeah, either you use a glue or nail or screws or concrete or something. Okay, got attached from one part to another. Same thing as that. The elements. Okay, they do it by themselves. They have their own life. Those lives are called chemical life. They have their own ability. They can move, and also they can pick up a potential by aggregating with other atoms and other atoms and different elements. So that we call it another term, bonding, right? So if you think about bonding, do not understand there's a little bit of differences in regular bonding and that level, okay, material, which is elemental and atomic level bonding. Sorry, the nature is, even if we use the word chemical bonding, you might always think like they're rigid, solid, and they're fixed and permanent. Okay, but that is true only when you perceive at our level of life. Okay, when you study at their level of life, meaning like the elements at their structure, basic structure, the bondings they're just colliding, and sometimes accidentally fit. And when they fit, they don't have enough energy to get back out of it, so it stay. Okay, so when that happens again and again, from our level of light, we see that as aggregations. Okay, you see that as some sort of material, wood or plastic or some sort of fiber, or you can see, like alloy, the metal material, like etc., things like that. So again, we have materials. We have ways to connect these materials, and we call them bonding. And everything that you're seeing are in a structure, okay? Some of the structures are ordered, repeated pattern, some of them are not. Some of them are just randomly aggregated, and then every time these elements are in a particular structure, they have their own properties, and we can use them. Yeah, we can use them. We've been doing nothing but using everything we've got in this world. Yeah, that's what we do. But we have nothing else, and then you do not have anything more than what you have. So you have to use whatever you have, right? And we are very good at it. All right. So 8 of them make up 97%. Okay, of our Earth substances. So if you take a look at it, go outside and you pick it up, they're always composed of aluminum or match, okay, like aluminum ion, calcium, sodium, silicon, oxygen, magnesium, potassium. So all the products that we make okay, are usually composed of these things. So you cannot go wrong with it, and we're mastering all of that already. Okay, so you have your aluminum, iron, you have your calcium, sodium, silicon, you have oxygen, magnesium, and we have potassium. So our time is right now we're playing with lights. Okay, we're getting into, we know how to handle lights and use it. So we found out about how to use light to store past activities. Okay, only images that we can store, and movement of the images, because we now know how to move the images by using lights particles. So that's incredibly powerful techniques that we found, like past 3 or 4 decades, um, and very powerful, very very powerful. And some people just take it for granted. Some people are seriously getting into it to understand more and more about lights, because lights is for now it's for us, we need it, okay, to live on, because if you take away the light rays, photons, we will be energyless, okay, because our body needs it. Our kinetic energy also needs it, okay, for us to be able to have colors, and vision depends on the photons, okay, which is your light particles. Without them, the world is always it's colorless, it's dark, okay, and cold. You can't be able to perceive in the colorful way. Okay, so that's a pretty serious serious phenomena that we have, that we all take it for granted. But then in science, we are studying systematically. We've been studying lights systematically. We have many different kinds of light, right? And we're using it so that we can be able to know what else is there that we don't know. Okay, so now going back here, for midterm exam. Okay, midterm we're gonna do paper. For final exam, we're gonna do fun thing by building our own product, by choosing materials carefully, and you will document it. Okay, and I'll show how to do it. So the first midterm exam, I will definitely ask you, okay, all of this, so make sure you get that. So we now know we have elements, and elements are composed of atoms. Okay, and we can measure the weight of a single atom. Okay, I don't want to go all the way back and explain all the history. You should know about it, okay, because you have already passed high school. If you haven't, I'll try to please go back and read the history of how we, okay, come to this point to weight that. Okay, usually you have to take chemistry 1 and 2, okay, to go back to this. So anyway, I take it you have an understanding of how to how to take the mass of the atom. They will never let you do it, but it needs a sophisticated machine to do that. However, you will definitely know how we did it from the textbook. Okay, and I'm not going to take time to explain that again to you. So just you deal with your chemistry 1 and 2. Okay, it's in there. So atomic weight is just a relative weight, okay, of the atom. We don't have an absolute weight because, like I said, the atom is very, very small. They are in the very negative, 26, around that area for some of them. So you're dealing with the negative exponent, okay? And they're incredibly small. So in your brain, don't just stay at our level, okay? So we're like, our weights are between like maybe 50 pounds, and some people are very heavy, so they go like maybe 300 pounds probably, okay? And then standard deviation. So just like that, we try to measure, okay? We go by using sophisticated machines, okay, and tools to get the weight of the atom, and we got the relative weight of it, okay, not the absolute one. And we have determined that weight, okay, and that is complete. Since it is a relative weight, you have to come up with something that you know, okay? So what we know, we have oxygen, and oxygen, we have 16 AMU. All other 110 elements, okay, are composed of atoms, and these atoms, each of their weight are relative. They are relative to this, okay, oxygen weight. And again, AMU is nothing but we call the atomic mass unit, okay, it's just a unit, and oxygen has 16 of it, okay. So what are we weighing, what is the substance of oxygen? So we're actually going smaller particles than atom itself, because atom is also composed of very tiny, tiny, tiny particles, okay. So atomic weights, we measure it with AMU. And another common units that we call AMU is daltons, okay. So if you hear daltons, you understand that's the unit for the weight of an atom, yeah. So atomic weight is very fundamental to chemistry, and chemistry is the core of the materials, okay. And our field is right here in industries, and we use this, so therefore you have to know this, okay. Without the foundation, without knowing the fundamentals, it will be very difficult to manipulate at the materials level. So you have to know the internal structure of each one of them. And materials are nothing but they're composed of one or more elements. Elements are composed of atoms. Okay, atoms are composed of smaller particles, and we're going to get into this. So this is just a little chart introducing you what the numbers are. Okay, so we usually box it. Okay, and here is an example how we describe an element, and that's Fe is ion, and F is just a symbol, abbreviated, so you don't have to write long, okay, very long letters. We usually use simple and short text in science because it's easy to handle and also easy to remember, okay. So if you write like IRONIN, you have to write it again and again, and your brain remembers FE better than IRON, okay. Because again, brain is running with the natural electrical impulses, and these electrical impulses are made of these tiny particles composed of your atoms. So whether we're living things or non-living things or materials, different kinds of elements, okay, all the way down to the fundamental, we're the same. Okay, we have protons, we have neutrons, and they are completely moving inside of your system, okay. And that's our true nature of it. So if you want to be connected to God or connected to the universe, connected to all these big things that we talk about, you've got to pull your mind from this level all the way to that fundamental level. And you can do it. Some individuals who have incredible focus, concentration can do that, okay? It's not theoretically, that's for real, okay? Example like Buddha, example like Jesus, incredibly intelligent people who can understand inside out of their own system, okay? So, but then when they explained it and when you interpret, there goes the issue, because people have different brain. and they are interpreting differently. So we understand very differently, from deviated from the original stuff. So you gotta go back. Even the book we talk about Bible, the Bible book is little book, right? And you can finish it within an hour if you read it. But you ended up don't know because you have no idea who say what and how that's been said. You have to sit down and think about it. That's a difficult thing, yeah? And you end up in the way you understood, which is very, very, very deviated from what's been totally told you. So anyway, so science and religions actually is the same thing, yeah? We're studying because we have nothing more than what we have. There is really nothing more than that. This is it, okay? This is it. So here your iron, and then this is 26, and that's your atomic number, okay? Number, not atomic weight, that's the number. Atomic weight is right down there, right there, okay? So that's a 50.5847. So some student gave me like grams. That's not grams. It doesn't say anything. It's in a box. So every time you're in a box, okay, usually come from the periodic table. I'm going to see it in the next slide. And this is just telling you, the weight of this element. Okay. Don't think like one single iron atom weighs, okay, 55.847 gram. Gram is a real big thing, okay? So ridiculous. I have to tell you that because some student come up with that. Oh my gosh, no matter how many times you say that. So anyway, the weight is based on 16 AMU. So atomic weight unit is AMU, okay? Sometimes we call that daltons, 55.847 daltons. Relative weight. Don't forget relative weight. Okay? Okay, so let's go to the next one. Now, since we now know there are 110 elements found, discovered, okay? And some of them are created, most of them are found. They're arranged in the periodic table. So we usually, in science, we usually collect the data and then we organize the data so you can extract the data anytime you want it. When you store it, you have to store it systematically. So therefore, when you take it back out, it's going to come out systematically. Okay, random, it's not very good for scientific knowledge, okay, collection. So you systematically put, systematically take out. The same thing when you're studying something. Don't just read blah 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 blah. You have to put it into your brain, step by step, okay, systematically, in order. You can make that order by yourself. So why is because our brain is functioning with its own impulses, okay? It's not a constant thing it goes like one group and then another group and then another group, and there are gaps in between that group. So sometimes when you think about it, you remember only a certain point of activity in the time, okay? Then you forget everything else, right? Because that's all, when you put it in, you put in too many, so it's just your brain, okay, it doesn't get it, all of it. It only get like that, this, and that, and then neglect everything in between them. Same as your eyesight. Eyesight, the same thing. It's not continuous. It's going from point to point. So therefore you think like, I saw everything. No, you never see everything. You see points, okay? And your brain is connecting because you have look at maybe the same room. How many times you get up in the morning in the same room, right? There's that many days you get up. But then you're not seeing the whole room. You're seeing this point today and that point after 3 seconds later, and then it's just like right in there. Every time your eye moves, okay? It's a pretty funny thing. It's so also very interesting. So anyway, so element, we're going to arrange them. We're going to put it in systematically so we can take it back out in the way we want it, whenever we want it. So we make a periodic table to put these elements. So all elements are ordered and then recorded, okay? That's just showing you the hand-on figure thing, doesn't really matter. So the elements are arranged we arrange them in ascending order, okay? Ascending going up. and rows. So the table always have rows and then columns. So I don't have to do that. Everybody knows rows, yeah? And then everybody knows columns because it is a table. So what are the cells, yeah? The atomic number is, again, the number, the first letter that you see in the little box that I just showed you in the previous slide. Okay, this number at the top. So atomic number is nothing but that's just a number of protons. Okay, an atom is made of nucleus at the center. Okay, and you have certain number of electrons. Okay, hanging around that center. And you'll find particles of protons. Okay, light particles are called photons. This one is protons, so don't confuse that two either. Anyway, so protons in the center. Okay, that's nucleus, we call that. So photons are the number, and we are giving a name. We call that atomic numbers. Yeah. Nucleus also have other particles with the protons, okay, and I'm going to show you what they are later. So this is just a sketch, okay, and human draw this, okay, but this is like what you can see by using a machine, okay, so different like we cannot be able to see at this level with our naked eyes, okay, cannot. So you have to use a special tool to be able to see this. So here is we have a single atom. The physical structure looks like that, nothing but a little shiny little thing right there, tiny. Okay, and then this is what you see with the help of an instrument. So you're gonna see, because we use a light so we can see it at that level of structure. So here is your nucleus, okay, and then you can find this little chunk. This one actually come off of the nucleus, okay? But then it can go farther than that distance. Depends on the size of this nucleus, okay? So at this level of structure, they have something called force, okay? Force, momentum, force. Speed, we call it velocity, okay? So they are the governing phenomena in that, okay, level of structure, and they're just hanging there. So some particles come off of it, and we call that electrons, and it can't move farther than that. Okay, it will stop at a distance. So for hydrogen, one electron just hanging right there, and then going around, not in 2 dimension, it's going around like in a sphere, okay, 3 dimension, not perfect sphere. It's sometimes dent here and there everywhere and become a loop. Sometimes the shape is different, okay, but then we assume spherical, and you can find that particle going around this, okay. So that's the very small, okay, structure. And again, our universe have nothing but the objects floating, hanging, or moving around. And at this level of structure, the same thing. Particles hanging, taking place, okay, or hanging around, or moving around another particle. And that's our true nature. Okay, so we have two major energy. Energy is just a word. In common English word is ability of an object or a thing, okay? So everything that we have in the universe can do two major things, okay? Whether they're living structure or non-living structure, they can move, okay, on its own or with the help of something, okay, usually physical forces. And they can stay, potential energy, okay? They can stay or hang. Some professors use the word hang, some professors use the word floating, some professors use the word just take a place, okay, in the space. So in order for something to stay in a position, it needs energy, and we call that ability to stay in that position, potential energy, okay? So that's all it can do, okay, in this physical state. So now we're going to go back here. So that's about hydrogen. So you look at the single proton. Number of proton is atomic number. So the atomic number of the first element, hydrogen, is 1. Okay, so 1 proton in its nucleus. So an element's position in the table. Okay, so this table is not like whatever table. This table is a thoroughly thought and thoroughly designed table. Okay, so this table is actually showing you the structure of the atom. Okay, and we put them in order for all of the 110 elements. Okay, so if you take a look at the cell of the periodic table, you will have an element name in it, and it also tells you everything about that element. Okay, the position, which is this little cell box, where is it, at which row, and at which column. Okay, and we can be able to draw just by looking at the periodic table. So that's why at high school, if you take like chemistry, right, and you go and do your exam, final exam, whatever, or the standardized exam, and you're given periodic table right there. That's the answer. The answer is just straight right in front of you, nothing to remember. Everything is right in there. And if you know how to read it. Okay. Alright, so let's go back here and then erase this. No, I'm gonna erase that as well. Okay. If you are a person who want to read the entire textbook handout, you can do it, but then concentrate on what matters to your major. Okay, which is these important key points here in the lecture. Alright, go to the next one. Okay, so alright, so here we have 3 information, and it's talking about the very first one is the number of protons. The protons is the number of little particles at the nucleus. Okay, so we can draw that. Where is the nucleus contains certain number of protons. So for iron, we have 26 of them right at the center, protons. Now this iron weighs, okay, 55.847 AMU or daltons. Okay, that is based on oxygen 16. So now we go get into this periodic table, and we have rows. They are in ascending order of electrons. Okay, you can also go with protons. Okay, so I like to read the cells. I always go electrons. But then some people love this little number, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But when you go to grad school, you change the way because electron matters more than the protons. When you look at the cell box, that's an electron. Okay, so here, but right now, let's just go back to our high school simple one. So that's we're going to start with 1 single proton for hydrogen, and you have 2 protons for helium. Okay, and hydrogen is 1.008 AMU, 4.003 AMU for helium. So this guy is bigger than that guy. Okay, about 3 times bigger. Yeah, because it's more powerful, because it has 2 particles at the center of the nucleus. And you have already known some of the physical forces. So if you have objects, okay, in the space, and you have another object in the same space, they have, okay, they always have some sort of interaction. Okay, you can see them, you can feel them. It looks like they're not reacting, and there is a distance in between them, but they always interact. Okay, but at our level, we can feel it. So here I am sitting here, and suppose you're standing over there, your material, okay, composing your structure always interact with the next person's, okay, material compose their structure. And we cannot be able to perceive that. Okay, those are the laws of the nature. But at the element state, at this level, okay, very, very, very small, tiny little structure occupying very tiny little space right there. And that forces between them, okay, is their power, okay? So they can attract and they can feel, okay, this particle and that particle interaction, they can feel it, okay? Each particle very close to each particle strongly, okay? So that's why we call it attraction, we call it repulsion, okay? And all of those are, again, the physical forces, okay? Physical phenomena right in there. And anyway, so we'll continue to 3 and then 4, then 5, 6, 7, 8, 9, 10, 11, 12, 13, all the way. Some high school teacher want you to memorize all the way from 1 to 20, okay? And they might tell you to write everything and memorize. You can do that too, okay? But it's not necessary for it industrial material, okay? Because we never try to remember anything. We only learn how to apply and use them. Because you're at the level of application, okay? Not memorizing things anymore, okay? Because you have to make it happen. You have to do it and make it happen instead of understanding it. Understanding stage is over, yeah? Okay, so we now know the rows are nothing but adjust the position, okay, of the little particles that can come off from the nucleus, and we call them electrons, okay? So that's just an imaginary line. The real physical thing is a sphere around, and they have some other lobe structure, okay? It depends on the pull or repulsion of this nucleus to these particles. So if you think about helium is right here. That's the 2 protons right here, okay? 2 protons right there. So right here you can see that's 2. And the boxes are, like I told you, those are electrons. So you have 1 electron and then you have another electron, the cell. The cells are electrons. So I have 2 electrons, okay? Occupying in the space. We call that the very first, we call this little line, but it doesn't exist in 2 dimension. It's actually like this, okay, like a little sphere all around the center nucleus particle right there. And these electrons are very, very small, okay, compared to the proton, very small. They just gone around, and it's really difficult for spot it, okay, even though a very good machine. It took them like for many, many years to be able to trace, okay, the electrons. So we always use a probability of finding the electrons. We don't know the exact, can never know the absolute location of it. Okay, it's like angels, like angels. I usually describe, this nature like angels because they're just moving around so fast, like little light can go on like ding 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 like that. And shining. I usually call this little star inside of the structures because it's very much like that, okay? Powerful, very, very powerful. And they're so crazy, moving around. So anyway, so helium, 2 protons and 2 electrons. How do I read it? These are the proton numbers. This box, okay, you can call it box or a cell, that's electron, 1 electron. Second box where helium stands, 2 electrons, okay? So when you see helium, we already know there is a 1, and then we go up to helium 2. Because their structure is just a 1 center nucleus, and then you have some particles hanging. And then inside of the nucleus, there are particles, we call them protons. And the hanging things are called electrons, okay? and this little electron actually come off, okay, from the center. That's why we call that electrons are negative, okay, and then we give the proton positive. So if you put that back to the proton, you get a neutron, okay, neutral back again. It's just like, why does it come off? It's because it's floating in the space. They also have wear and tear. So the formation of electron comes from the wear and tear of that nucleus particles. Okay, they can go away from there because they're so small. So the force that this can exert, it won't let this particle go off. It just hang right there, like the moon. Okay, our moon hanging around our planet. That moon, it breaks off from something before. Okay, but then it won't go off into the space because of a pull from our Earth. It just hang right there, just like that. Okay, so when it come off, you have two chunks. One chunk we call it positive, and some students think like positive is some physical, charge right there. Oh my gosh, no, that's just a word. We call it charge because they can move. Okay, so when something break off of something, it looks like that, right? And then let's say, and then we call this chunk negative, and then that chunk positive. It's just a sign, human language that give it to it. Okay, the physical thing is like a little tiny two parts. That's it. One come off at a point. Okay, you can put it back in, and they go back to neutral. But of course, theoretically, technically, we can think like that. But then physically, it is very difficult. You can hold it or push it or simulate it to go back, and you can do that. Okay, but then it's the theoretically is. So if you put this back in, you got the neutron back. Okay, and they become settled, meaning like if you have two particles, they're smaller than the original particle like that. So it's a bigger mass. Bigger mass, it's settled down. Okay, smaller mass, they can move faster. Yeah, since because this breakage is going to give them energy, kinetic energy. So with the force, it's going to push that out. So therefore it goes. Yeah, and we call that being charged. Being charged. And if you put that back in, they gain mass. So become bigger than this little chunk. So therefore they settle down. So meaning like they become lower in energy. So therefore cannot move. Okay. Go back to the potential state, or we call that the stable state. Yeah. All right. So anyway, trying to review everything back for you. I believe you remember now. And then we go and do the same thing. So we know how to count the protons. We know how to count the electrons. Okay, by just looking at the periodic table. So if you see, this is hydrogen, helium, lithium, beryllium, okay, boron. So if you look at the boron, oh, we have 5 protons, and then you're going to count how many electrons. So 1, 2, 3, 4, 5 electrons, okay, and then it weights is that. Yeah, the first row we already show you, it's kind of like a sphere shell, and we usually draw like that, right? As energy, called the energy level, but it's just a place where the electrons stop because it doesn't have more energy than that. That's the maximum energy it acquired by breaking off from here. And this gravity, okay, is going to pull that back, and then this going around, hang in there, okay, hang in there. It can get back, it can find the right path back to the nucleus because it's too small, yeah? So this force is literally pushing it and leaving it outside going around. A really crazy phenomenon. So anyway, then you know how to put the, it said, go ahead and put the 2 electrons, okay? And that's the amount it can hold. The rest of them are going to scatter to the second, okay? Second space, which is like this much. So we will have 1, 2, 3 electrons, okay? 1, 2, 3 electrons in the second, we call that orbit because the way that we draw looks like an orbit. We call that shell, okay, because it is not a two-dimension, it is a 360-degree all around three-dimensional, okay, space. And again, not only in the form of sphere, they also have loads, okay. And we use a probability of finding electron in these locations because we never know the absolute location of these little tiny electron particles. So anyway, now you know this is a second, okay, that's a second energy level. This is the first. Second row is second energy level, meaning like a distance away from the nucleus, okay? Distance away from the nucleus. 5 protons. There are 5 cell boxes there, so therefore 5 electrons, okay, occupying that 2 shells or 2 energy levels, okay. That's the maximum it can hang right there, okay. And so, okay, but nobody, I'm not going to ask you to answer all of that like in high school anymore, okay. We're done with the periodic table thing. And here's a little gap right there. It's just telling you that in between, okay, these guys, there's a whole bunch of elements, and that's this, okay? Yeah, and let's go back in here. So it's done with a review of your periodic table. So element, you can read everything about it. You can Google it if you want to know the entire, okay, word of each abbreviation. That's a platinum, okay, mercury, titanium, okay, lead. So and so and go on. And go back. Okay, so this is an example structure, okay, of a bigger atom. So we chose 86 for radon, okay. So you have 86 protons right in there. And here we start to show you the map of the electrons, okay. So there are 86 electrons. So the very first orbit is your first shell or first energy level. We have 2 of them in there. Okay, and then we have second, we have 8, third, 18, 32, 18, and 8 electrons spreading out. Okay, but then they stay around the nucleus. Why? Because of the attractions, yeah, or gravity, you can call it, and hang, yeah. But if you have an external force, it might come off, okay, and then go into the other orbit of the other atom, okay. And they're not finding it, just like bump here, bump there, meet other atoms, and then this electron might, okay, go and visit other atoms, kind of like visiting other people's house like that. And the other electrons might come into this shell, okay, and that's the beginning of bonding. We call it bonding. Bonding is nothing but it's just the real phenomena. It just come off, okay, because another one to come a bump, so that the force usually kick you out of your original shell. And once you kick out, you got a little bit of energy, and then you float around, and then you hook up again with nearest, okay, nearest orbit, and go into it. And so whenever they do, we have a structure, okay, and you can see these properties from the outside at different levels. Again, life is at different level. You're not living only one life. You're actually you at the organism, meaning like we're the end result of our organ system, okay, system of organs, and the organs are composed of cells. So you're living at the organ state, which you can't feel anything, but then you have a part of the mind that oversee only internal reactions, but we call the unconscious mind. That's satisfied. Like when you're hungry, then you have to go and eat. You think like you are eating. No, it's your body. Okay, another mind is making you eat. Go ahead and just like close your nose or something. You can't hold it for more than 2 minutes. Okay, your body is gonna force to remove your hand, and you will stop breathing. Okay, so those kind of control is not done by you. It is done by your body system. Okay, something that you can control is beyond our control. So make sure you realize that you're not living. Okay, your mind is not the thing that is controlling your body. Okay. there is another mind that is controlling, watching the system of your body. And then there are cells that are controlling the internal processes of your body, okay? And then inside of the cell, there are many more, okay, complex. A cell is already like a city inside, okay? And they have their own things going on, your DNA, okay, and many other different proteins and particles doing their own work, and you're living at that level as well. And these ones are way to the fabric of this universe, okay, material, and you're also living at that level, okay, not with the nervous system. Nervous system is only at this bigger level, which is organ system level, yeah. So make sure you understand all of that, okay? So review chemistry, review physics, review everything, and know where you are, at what level, and how you're functioning, okay? All right, let's go finish with the big atom and structures and show you the shells. So I already showed you the periodic table, and we have rows right there, and then the columns, okay, and then these little boxes are electrons. So rows are known as, we call them periods, okay? And they are organized. And then by number of electron shells. So first row is first shell. Second row is second shell, like that, okay? It's not a very perfect drawing, but you got the idea. And here is your nucleus right there, okay? Probably I should use a red one for the nucleus, yeah? And then electron for the red one, blue one, right? Electrons, yeah. So electrons are, oh my god, this is so big. And then here too, okay. And then we call these ones electron shells. It looks like a shell. It's a 3D. Again, we're drawing 2D, but they are 3D, three-dimensional. We call them orbits, yeah, around the nucleus. And you can find the electrons. The columns right here, and we call them groups, okay. And we usually name them in Roman, okay, numerals, like 4A, okay, column 4A is a group. And no need to go back into details for any of that, okay, just know that the columns are groups, and they are classified in Roman numerals, right? Again, what's the goal for that is, again, they were going to contribute different structure, okay, different structures. Depends on the number of electrons and protons. So now we go back to atom, and then we're going to take a look at what's ion. So when you look at the atom, it's just a small part, okay, the smallest part of the element. Just like the basic unit of life, it is a cell. Same as that basic unit of an element is an atom, okay? And why do we cut it off right there and we don't go into quantum level? Because when you go into quantum level, we don't get the same physical and chemical properties anymore. It's a completely different nature, yeah, different forces, different nature. They don't behave like the natural forces that we know, okay? So this is our smallest element structure, and we call that atom because they maintain, okay, the physical and chemical properties. That's the smallest ever. So an atom is, when you take a look at it, they're all balanced together. It has to be balanced, okay? If it is not balanced, it won't, you can't, that structure is not going to be there, okay? It will just break. It will break. So the nature has a way of finding stability, okay? You always try to find these little tiny particles, always try to find a way to stay, okay, in a space. So they appear and then become a structure as soon as they get all of the, okay, certain particles together. These are just a little particle going around, and then all of a sudden, out of nowhere, they, come to a structure like that. And as soon as they come to the structure like that, you start to get that property and chemical and physical property, bang, appear. So the beginning of our side of the universe that you started to understand okay, the appearances of the particles, appearances of out of the fabric of this universe. Looks like nothing, a darkness, nothing, and then here we go, bang, come up, yeah, and structure appears. The structure appears only when it gets a stability, okay? How is it stabilizing? They're stabilizing with certain number of protons and electrons, and there's something else to call neutrons, okay? The cushion material. And so it's just right in. So it's a balanced state. It's got to be balanced in order for it to stay in a potential state, okay? Potential energy with a potential energy state to take a place in the space, okay? You have to be balanced. And that's what we're stressing here. An atom is in a balanced state when it has the same number of electrons and protons, okay? Now you want to know, what if we don't have the balanced one? So now you got like a 2 additional, right? 2 minus. So when you look at it here, 1, 2, 3, 4, 5, 6, 7. So here when you count it, 1, 2, 3, 4, 5, 6, 7. Okay? And you have 2 more right there. Yeah? So 1, 2, 3, 4. So you have 1, 2, 3, and then 4. Additional 1 here. Additional 2 here. Yeah? So therefore you have 2 more. 8 total. 2 more. Makes it to 10. Yeah? So 2 electron, extra electron. So therefore we put a sign right there. Hey, I am oxygen, but I have 2 extra electrons in my orbit. Okay? That I'm holding with my nucleus. So we call that oxygen 2 minus. So if you see that, you know that oxygen is not in a balanced state. Okay? It's completely unbalanced. And we call that kind of unbalanced state ionized state. And some people call it uncharged. Yeah? Why is it charged? Because of this unproportional thing going on. This guy is not going to take place in the space. It's going to move. Okay? It will move more than it can move before. Okay? So that's why we call it charge. Nothing but they have extra. And that extra is not balanced. Okay? Why? Because it's just disturbing this nucleus. A nucleus got to put more, and it can put more energy, okay, to attract and keep them stay stable, so they become agitated and start moving. Yeah. But when atom is ionized, okay, they're gonna either, since they cannot balance, the nucleus cannot balance, it cannot, so they're gonna either go somewhere else and, okay, find these extra electrons to get into someone else's shell. So you might have like, you might see like it's gonna make, if it bumps into hydrogen, it might get like 2 water molecules, okay? So you need 4 hydrogen to bump into oxygen, okay? And 2 of them might take it, okay? So 1 electron will go into hydrogen's shell, okay? So it will become like H plus. So this thing will go and share, okay? Then it, I wouldn't say share, okay? It would just like hang in there, okay? 2 more. So meaning like another 2 atoms can come and stay with this guy, okay? To balance it. And we call them, ionized state. And it can react, okay? Either lose or gain valence electrons. So valence electrons are nothing but these electrons in the outermost, okay, in the outermost shell. Yeah. So ionization, when does it occur? Okay. Well, it always happens because they're all going around in the space. In the space, there's so many other atoms. Okay. Then they bump into something and then they're going to ionize. Yeah. Pretty easy one. Why do they ionize? Because they are moving, yeah, and they're forced to, they have some certain pressure, certain momentum, certain like little tiny bitty bit of velocity, okay? All of that physical forces contribute to the ionization state, okay? And so what are the miracles? The miracles are they take structures and then they combine with other atoms and make more structures. Different structures they make, different properties and different chemicals we get. Okay? Here we go. Since we now know how a structure is formed, we can be able to make them in the lab. Okay? We can make like we start to do from the metal one, okay, because that's easy to handle. Oxygen gas state is more you need more and more sophisticated and powerful, okay, tools to be able to. But the technically, okay, theoretically, how do you make the things in the lab is put in the protons, electrons, and then force them to react, okay, and then you see the miracles. Ah, there. Oh, there's my sapphire developed in the lung. It takes the nature to make it long time, yeah. But then they're not the same because the lab sapphires are very very light and they don't have the natural, okay, composition. It's just too shining and too flashy, okay, and too new, yeah. So you can make it, but then they're not the same. Naturally made has something called time in it. Okay, and lab means that you don't have that time. Okay, so the quality is different, even if the structure is the same. Now we will review molecules, ions, and atoms again. So molecules they're just like, okay, we now know the atoms are composed of protons, neutrons, and electrons, right? Ions are you have either more electrons or less electrons and become ionized, okay? Molecules, when these atoms or ions, they group together with certain bond, okay, we call them molecules. This is like they come together and you have a molecule. So we go back to the oxygen example with the oxygen O2 minus is going to meet two other hydrogens, okay, atoms floating around, and this means that this hydrogen, okay, don't have lack of electron is usually indicated by a positive sign right there. Okay, doesn't mean like it has a positive charge. So if you say like hydrogen has a positive charge, you will be thinking the charge is a physical thing that is attached to it. No, not like that. Okay, it's just lack of electron, okay, around the nucleus. So hydrogen without the electron, okay, want the electron, okay, and the oxygen with two extra electron, okay, and that electron can float around this hydrogen nucleus if the hydrogen's ion is going to be in the vicinity of this oxygen 2 minus ion, okay. So here is a very simple diagram showing how the electron of hydrogen can go and visit into this orbit of oxygen, and it can also go back into hydrogen, okay, orbit. And why is it doing that? Because of this nucleus forces, okay, pushing, pulling, pushing, pulling, and they go, yeah. So two hydrogen and one oxygen, we call that a water molecule, a very basic one. Very, very basic one, yeah. So one molecule of water contains 3 atoms. So 2 of them are hydrogen and 1 of them is oxygen. Okay, so you got the idea of what a molecule is. Group of atoms and ions, yeah. Isotope. So when you take a look at the nucleus, okay, you're going to have 2 component. One is called proton and the other one is called neutron. So a nucleus is made of proton and neutron together, okay? we call the neutral the cushioning material. This is there and then neutral, okay? And if you have like an element, and here we're going to give example of your isotope. So we pick carbon. So when you take a look at the carbon nucleus, you're going to see like, okay, they have different number of protons and neutrons, okay? They have the same, so carbon 12, 13, and 14, same proton numbers, but they have different neutron number. At that time, we're going to call them isotopes. So the nucleus, okay, can have different numbers of protons and neutrons in a condition in which they have the same number of protons but different numbers of neutrons. We call, okay, these atoms isotopes. C12, there are 12 particles, okay, in the nucleus. 6 of them are protons and 6 of them are neutrons. Carbon 13, in the nucleus, it has 6 protons and 7 neutrons. Carbon 14, in the nucleus, it has 6 protons and 8 neutrons. Okay, see how different the neutron numbers are? Even if they're the same carbon, yeah? And we call them isotopes. Anyway, so now this is, okay, it just showing you carbon 12 is pretty stable. Carbon 13 is pretty stable. It's not very different. It's pretty balanced, huh? But this one kind of balanced. This is too many, okay? Too many neutrons here and 6 protons right there. So that just completely unbalanced the structure. And in this case, we call carbon 14 radioactive, okay? And you don't see this a lot, so this trace. This is like about 1.07% of carbon. And this one is 98.93% of carbon. They stay in this stable state. Okay, so you can see them and use them. This one you have to handle it with care because they are radioactive. Okay. Now, when you take a look at the basic component of an atom, we already understood there is a nucleus at the center, neutron, and proton, okay? And there is electron particle, and that particle is at a distance from the nucleus, and this distance is determined, okay, by the size of that, and by the forces, okay, governing this, okay, and the ability that this can do, okay, whether it can move or it can stay, or how much it can attract or repel, okay? But then we're not going to get into mechanics or physics. So if you can get the very basic structure of it, we're okay in our field, yeah? And here that's the imaginary shell. It doesn't stay like that. This is not natural, okay? It's like a sphere like that, okay? This thing going around. And if you're lucky, you can find this electron. You can locate it. So now we know there are shells away from the nucleus, and they can, okay, they can contain a particular number of electrons, okay? You can put like too many in there. You can put only 2 in the first shell, okay, and 8 in the second shell, so and so. So when you take a look at this, all right, outer energy shell in an atom, and if that shell is filled, okay, filled means filled with electrons, so there is no more space for any other electrons to come in here. We call that lowest energy, okay, lowest energy state, because they are stable, completely stabilized with these forces. And we call, you know, these shells, the outermost shells, okay, the valence shells are and that condition we call inert. Okay, the conditions of the atom with filled valence shells are inert. Okay, inert means they're very stable. They don't react or they don't move too much around. Okay, and also they don't interact with other atoms, nor they have available space for other electrons to come in or their electrons to go out easily. Okay, so therefore it is inert. So when you take a look at this, what is this? Yes, air. So nitrogen in the air, okay, is inert. If nitrogen in the air is not inert, we're gonna be doomed. Yeah. This is completely inert. It's not reactive. It's just there. And again, we call them uh, cushions. Okay, cushions of the air. And the air also has oxygen, and then it has other stuff, which is carbon dioxide and the water, which is H2O, usually in vapor, sometimes liquid, and other trace gases or particles right in there. So if you think about air, you think like that's oxygen, oxygen. No, not really. Majority of them are nitrogen. Okay, that doesn't do anything to you. You can, okay, because they're just like very stable gas in there, and they're not harmful to you. But if this one breaks, okay, and for some reason, okay, laser can break this nitrogen, okay, and also very energetic, okay, lights like laser can also break this, okay, nitrogen. And if they form nitrogen dioxide or nitrogen oxide, our world is gonna be so screwed. Okay, we don't want that. The oxygen itself, without heavy nitrogen, is not good for the world because oxygen completely supports fires. Okay, it burns. So we don't want this a lot either. So 21% is pretty good. 78 to 80% more or less in some regions. This is just average of the atmosphere. And things that we're so worried about is there, and they're very critical. Okay, because you can't have more than 1% of it. Okay, and if you have more than 1% of it, we are pretty screwed again. Yeah. So this carbon dioxide coming out from our cars, the factories, okay, appliances, etc., etc. And we have to be so careful about it because you can put too many molecules of carbon dioxide into the air at all. We don't want to mess up with this proportions or percentages, and got to be again maintained at 1%. Yeah, and that's why everybody is so tired thinking about how in the world to get rid of emissions, to balance the emission, because we can't pass this little percentage right there in the air composition. Okay, it would be very harmful. Water, the same thing. Water vapor, we always think like the entire sky is filled with water vapor, right? Rain, you think about snow and all that. But actually this and this combined and other is only 1%. Okay, it's only 1%. So make sure that you understand what we have in the air. Alright, let's go to the next one. Now we will get into a little more into electron shell and number of electrons. So here, this is an example of zinc right there, the nucleus, okay? And you have shells. And again, I already told you we call them orbits, and they contain particular number of electrons, okay? We also call them energy level, and that's because these guys have certain amount of energy, which is completely completely proportional to the nucleus size and the forces around it. Okay, you can't put more than 2 in the first shell because that's the level of energy it can control. Okay, or it can have, I would say, according to the structure. Again, the space, the structure, the forces. And they always try to find, like pushing, and then bang, oh, I'm stable, pushing, bang, hey, I can't get, more than this many electrons, push it, hey, I'm okay, push it, and here, I'm at the number 4 share, and I can put only 2 outside. And I'm stable with the many electrons at the third, this many electrons at the second, this many electrons, okay, at the first energy level. It's just a distance, okay, this distance away, that distance away from the core of the nucleus, and that distance away, and then that distance away, that these electrons can float around. Yeah, you got the idea. So the outermost shell, we already told you, we call that valence, okay, because a lot of the interactions or the electron going out or coming in happened outside. It has to be outside, but it's pretty difficult to fill the already filled shell. Yeah, it's going to fill the non-complete shell first. Okay, filling mean like they're not doing it; they're just meeting and or become near to each other, and then stop and then go in, or just like come out like that. They don't really know, like they don't have the knowledge like we do, but then they have knowledge of space. Okay, they have knowledge of movement, and that's how they communicate. Yeah. So an atom can contain many three-dimensional energy levels. So when we say three-dimensional, do not fix, okay, in your head like it has to be always sphere. It's not like that. They go around in lobes. Okay, they go around in circular orbits, different shapes. And this table is just showing you the sub energy level. Okay, so we usually call either 1, 2, 3, 4. Okay, shell number 1, 2, 3, 4 going up outward, or we use letter energy level, so K, L, M, N, O, P, and Q, so and so. Okay, and then we have a shape. Okay, so we have S, and then P, D, and then F. Okay, these are just telling you like what kind of shape these energy levels are. Okay, can be able to accommodate. So in this S, okay, sub level, this shape can contain only 2 maximum. Okay, we have P. Okay, P energy level or sub level. Okay, at this shape, okay, we can, or space, we can contain only 6. For D 10, and then F is going to be 14. Okay, these are just abbreviation of the spatial configurations. Okay, just a sheet. And here are the maximum number that we're writing about it. And they're not like concentrating, okay, only in one shell. These are cumulative, by the way. Okay, so when you see 8, it means that there are 2 energy level, and the first one has 2, the second one has 6. Okay, so that will the maximum, the total for L has 2 level, K, and 2 sublevels, and the total number of electrons in that 2 shells, in that 2 sub-shapes, is going to be 8. Okay, 2 in the first, you can see that, and 6. Okay, in the P, and altogether 8. Okay, so here 1, 2, 3, 4, 5, 6, 7, 8. This is just showing 2-dimensional. They don't stay like that. Okay, the S is kind of like a sphere, and then the P is kind of like a lobe in the space. Okay, so they don't just stay flat like that. Okay, it's a different. So 2 sphere, and 6 in the P lobe. Okay. So now you can see that that's us, little sphere, okay? P looks like this little lobe, okay? And we have three-dimensional axis, and don't forget about that, your XYZ axis. And then your D, okay, that's the D orbit, looks like this, okay? Your P is right here, right down there. And this too is going to be your D, a little bit difficult to see it. Then your F looks like the little flower right there. Okay, and your electrons are floating, okay, or hanging away from the center nucleus in these locations. Okay, so you have probability of finding, when you go back to the previous slide, you will see the maximum amount of maximum number of electrons, and you can find these electrons, these places. Okay, just a configuration. So some student might have like some sort of interest to know the name of the abbreviations. So S is actually stand for, we call that sharp, and then P is principal, and D is diffuse, okay? And then your F is fundamental. But I'm not going to ask you. These are just a review for your chemistry 1 and 2, okay? We're linking these structures to the material, okay? Another one is to know how to calculate by using a formula. What do we want to calculate? We want to calculate the maximum number of electrons, okay, for any of the energy levels. So when you look at it, energy level 1, maximum you can hold. We already told you that in the table 2. Okay, and n equal to 2 means the energy level is 2. Your shell 2 can hold 8. The shell 3 can 18, and the shell 4 can hold 32 electrons. Okay, because it's farther away from the nucleus. Yeah. So this little n right here, that is just the number of orbits, yeah, from the nucleus. So since the electrons are going around so crazy in the SPDF shapes, okay, at each energy level, sometimes the forces from the nucleus cannot be able to reach, okay, and we call them like, oh, this electron is being shielded by that electron, and that electron is shielded by this electron, okay. It's not a permanent thing, it's always moving, okay, on and off thing. Shield and then expose, shield and then expose. So now we kind of understand the structure, okay, of atom. So now we're gonna get into when the atoms come together, how, okay, how this electron go in and out of other shell, okay, and their own shells, outside shells. We call it valence shell, okay. So the first type of bonding that we identify is when atom like this, okay, with like, look at this, just like you have only one electron here for sodium atom, okay, in the outermost or valence shell. And then this guy is like, it only needs one more to stabilize itself, okay. So when this atom, okay, come closer to chlorine atom right here, this little electron can be pulled, okay, into this space, vacant space. And that's happened because of this nucleus and also because of that nucleus, okay. They just fit in, just right in there, bang. And then it goes moving again, moving, so it moves here, very tiny little things, okay. It moves relatively. So movement is here, movement is there, and then movement is here, and it poof, and then bang, okay, switch to the other outermost shell from this, and then form ions like that, okay, but they're not separated like exaggerated drawing in here. It doesn't stay like that. It just hanging, okay. It just go ding 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 like that. So where this is like, we're trying to visualize by drawing diagrams, but the reality is these poor for light, okay, printed pictures like that, like, and you can only be able to see the density and reflection of certain lights. Okay, it's pretty neat. I always call them angels. Yeah, you can see them like that. So, all right. So anyway, this is sodium. Okay, plus ion, because its outermost electron is not right here. This guy has one extra electron, so we represent, oh, I have one extra electron. Okay, so I am a chloride ion right now, and this is sodium. Okay, 1 plus ion. Plus mean lack of electron, minus mean presence of extra electron. Okay, we don't really write 1, so minus meaning there's 1, minus 2 there's 2. Okay, so ionic bond is like that. By either losing electron, gaining electron, they form ion. If you get the electron, is a negative ion. If you lost it, you call that positive ion. Okay, and we're going to teach you which ion is what. Okay, where they have a specific name in future slides. So why do they do that? Chemical, okay, nature, or physics, okay, physical nature. Why do they do that? Is because our nature is always stabilized, okay, on its own, stabilized with other atoms. It's trying to reach, and we call it, in other words, we have a tendency to reach the lowest energy state, meaning we prefer potential, okay, meaning like taking a place to stay. Instead of moving around using kinetic energy, we stabilize ourselves, okay, to reach the lowest energy level by interacting with other atoms this way, okay. Ionic bonding by forming ions. Yeah, how do we form the ions? Bump here, bump there, and at one point you lost your electron. Why do you lose your electron? Because of the forces in the nucleus, because of the pull and push, okay, of these atoms. Okay, this is just showing you, look at this little, right here, this guy, yeah? This electron belongs to this atom. Okay, now it ionized and bonded, just hang that way, okay? And stabilize, okay, this molecule by these two atoms, and we call that ionic bonding. Okay, we're gonna link to material. So ionic bond, they're pretty strong. I forgot D here, but I'll put it later. And they're very, very high. Since they're very strong bond, you gotta use a lot of temperature or heat, okay, to melt it. So that's mean like very high melting temperature. You have to remember this. If it's very strong, you need more heat to break it, okay, or melt it. Hardness. They have low thermal and electrical conductivity, meaning like they don't allow the movement of electricity and heat on it. Okay, it doesn't allow it. Because the bond is too stable, meaning like it's completed. The structure is at its lowest energy level, so therefore it doesn't want to react with other stuff. Okay. So an example, this thing is a ceramic, okay, container, maybe food container or flour container. You can use any one of that. It looks like food container. So this is formed by ionic bonding in the smallest unit of structure, and we call that ceramic. It's just clay, and then you heat it, and you get those kind of product like that. So if you go to grocery store, you're gonna see flower pots. Go to Lowe's or Home Depot, you're gonna see flower pots like that. Okay, or whatever, food containers and so. Okay, so the common word is ceramic. There are many different kinds of types of ceramics. Okay, and ceramic structures are in the element name. Okay, molecule name, we call it sodium chloride, magnesium oxide, okay, and aluminum oxide. Okay, this is aluminum 3 oxide. Okay, so Al2O3. It has 3 plus charge and 2 minus here on this side. Yeah, this one is 1 plus and 1 minus. The same thing, 1 plus and 1 minus. Okay, this guy loses an electron. This guy loses an electron. This actually, magnesium is, if you go think about it, it's 2 minus, sorry. So 2 plus and 2 minus, 2 electrons. And this guy is 3 electrons, okay? And 2 electrons of this side. So lose 3 and then gain 2 here on this side. Okay, the next type of bond is called metallic bonding, and we usually call the electron cloud. So metals, they have atoms, okay, and with very few electrons in their valence shells. So if you take a look at metals like aluminum or iron or copper, you're going to see they have very few electrons in the outermost, valence is outermost shell, okay, of their atomic structure. So when metal comes together, these atoms come together, these electrons, okay, from the outermost shell is going to form electron clouds, okay? They're not going to completely lose it or gain it, like forming the ions. They don't do that. They only just come together, okay, and form electron clouds like that, okay? And these electron clouds move around in the material, and they're going to make these atoms stabilize. Stability is nothing but trying to, settle them down at the lowest energy level, okay? So, in other words, what they're trying to do is um, to, it's a very difficult thing to say. It's like, some of the professor would just tell you like it just formed the structure. So the nature is making structure on its own by itself. Okay, we lost the track of it because they're too small and you have no idea when they started to happen. Like that was long, 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 long time ago. Okay, way before way before our galaxy was formed, these things are happening. Okay, the appearance or the existence begin. Okay, the existence happened that way. Okay, they come together, they share the particles, they lose the particles, the all the little particles like this come together and then take a form, and there comes the existence with it. So that's the nature of these guys. It's been going on way before our our solar system. Okay, our solar systems. So this electron cloud movement, okay, is going to give you your metal's character, like good electrical, thermal energy, and you know how to feel the metal. Yeah, you go and touch it, and they usually is cold. Um, anyway, that all kinds of stuff, and come from electron cloud. So let's go next one. Cat ion and anion. So I was showing that one, okay. in previous slide, we have particular name for the ions. The positive ions are called cations, and the negative ions are called anions. Yeah? Don't get into confusion with the word charge. Okay? Charge is telling you where your electron is. Cat meaning lack, absence of electron, okay, because you're losing it. Anion, negative, meaning extra electrons, okay? They use a gain, a lose, okay, things like that. But I just take that there's an extra electron coming in from somewhere, yeah? Nearby atom in my outermost shell. So I can become stable, yeah? Neutral, you have both of them, meaning like you are in an original state. This is break, okay? Physically break off. And one has an electron, the other doesn't, okay? This is just a physical part. Okay, another type of bonding is covalent. Covalent, again, we're going to take a look at the outermost shell again. When the outermost shells are half full, they share, okay, electrons. Because it's so difficult to, get the rest of the electron in your shell, so why not just share, okay, with someone else to stabilize the energy to the lowest level. So again and again, our nature is trying to stabilize, okay? You're going to take or you're going to give. You're going to form a community and form an electron cloud, or you're going to share, okay? That's the way we bond. So your columns, right? Columns are, we call them group. So elements in these groups or columns, that's a 4A and that's a 5A, okay? So these elements, and you can see what is 4A and 5A column in the periodic table to get the name of all the element groups, okay? And they usually form covalent bonds to go to the lowest energy level so that they have a better structure, okay? So for example, diamond. Diamond is a natural material bonded covalently. So when you look at this diagram, you're going to see the atoms of carbon, okay? They are held together. This is a shared, okay, shared bond by the covalent bonding, okay, held together by covalent bonding because they're sharing without actually getting it or losing it like in ions. So there is a issue understanding ionic bond and covalent bond. You're okay about forming cations and anions. Now I'm going to draw that back again, okay? And we get like that, right? This complete transfer, okay, of electron. And then we have this chloride ion like that, negative, okay? And these atoms, I told you they hang, okay? They're not sharing the electron. They just completely form the ion. Once they form the ion, they hang, okay, together right there with the forces. But your electron, this guy electron is now here, okay, and this atom, atomic, complete structure, pull this guy next to it and sandwich it, okay, so there's another chloride atom here, so you see sodium chloride, your salt, okay, structure. Your little white thing right there. Yeah, when you go and put it on your mouth, it tastes salty. So anyway, it's like that. Okay. Covalent is different. Covalent is they are overlapped. Okay, they're just there, and this location might be here too. Okay, they go around, but then this is like black, okay, little electron will come into here, green, okay, little electron will go right in there as well. So they're going this way, and it's really pretty, okay, they're going like that. And like I say again, like if you can be able to access lab, okay, they're going to show you. Usually biochemistry or chemistry or biology lab, they have it, okay. You can go and take a look at it. So special, okay, microscope, very, very powerful, and you can see them with the lights, okay, and they're like angels, like popping up, kind of like that. So anyway, so like that. I'm gonna erase this. You got the idea of what's shared physically, and ionic bond is, the electron is in the other atom completely, even though the atom's still hanging around, okay? It won't come back in. And make sure you understand that difference. The last one is the secondary bonds. Now this one is molecules, okay, molecular bonds. So atoms to atoms, they stay with ionic, covalent, okay, bonds, and metallic. But for molecules to molecules, they're held together by secondary bonds. We call that van der Waals forces, okay? There's a big name, some guy found this out. It's attraction between positive and then negative, but this time is the word right here is molecules, okay? So the structure of polymer is based on molecules, okay? So the structure of polymer, if you think about polymer, it looks like this, okay? All the molecules hang around. Example, plastic, okay? Plastic is a polymer, it looks like that. It's a large molecule in long chain-like pattern. Wood, another example of secondary bonds. But for wood, it was a living thing, and then we chunk it out, and you see the fibers like that, okay? So inside of the wood, these are dead, okay? They live, but then over time they become hardwood, plywood, whatever. But the inside is like this, inside living, inside is like that, okay? That's dead. But you can still use it as a construction material board, or make, appliances, not appliances, yeah, some appliances and furnitures, okay? So that's between living material and become non-living later on, okay? But for wood, it's more like fibers. Okay, we don't really call like polymer, but then we call them like polymer fiber or fiber. If you try to mix with plastic, then you've got a plastic wood, okay, board. Like there are many of them. We always mix anyway because it's cheaper. Okay, I'm gonna erase this. I just wanna become better. I'm so sick. And go to the next slide. Amorphous materials. Okay, amorphous materials. We have solid, liquid, and gas material. For industrial materials, all of them. But in this book, we're gonna concentrate on only solid. Okay, but don't think like solid is the only industrial material. No, you're missing out on the other two. Okay, liquid and gas. Don't think like industrial materials are all non-living. No, living also included. And our recent example is virus. Yeah, we can make virus, and virus is an industrial material, by the way, because we can produce it in, where are we doing? In vaccines. Okay. All right. So solid materials, multi-billion business. Okay. We call that soft materials. Silicon, the same thing. Okay. Your chips, the same thing. Very, very little, very, very tiny, tiny, tiny transistors are made from tiny, 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 tiny industrial materials. Okay. And I think I was asking questions in the class, the live class, asking them if they know how computers store data. And I'm going to ask you back when I get better, okay? You have to know this, and that's pretty powerful. If you know it, you will get everything, okay? It's easy. We're playing, again, I'm going to give you a hint. We're playing with the photons, light material, okay? And something called switch. And the switch is very, 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 very microscopic, very small little switch that we can make by using lithography, okay? Photolithography, because you're using photons, so we go photolithography. Transistors can switch on and off. In your computer, we have only binary code, okay? 0 and 1. 0 is absence of photons, and 1 is presence of 1,000, okay? Amount of photons or numbers of photons. You can say amount because it's so small, or number of photons. That's all you need, okay? And we use the light particles come from your electricity, okay, photons. And your transistor, the switch, can go on and off just like 0 and 1. And everything that you can see, okay, in your computer, like they come in a big size, right? You always gotta look what's a 5 MB. That's a 5 megabytes. With 15 GB gigabytes. That's a lot of, right? And that many, okay, photons you're doing packaging or letting it go. But then they can go real fast because it takes less than fraction of seconds for the photons from the sun to get here. And from sun to here is such a very, very far distance. But it can get here, bang, yeah? So that's the amount of speed we're handling, okay? In the construction or the structure of your motherboard, right? Your computer. Cell phone the same, they get smaller and smaller, now it's smaller and smaller because we become more and more skillful building it, okay? So anyway, going back to here, so get back to our textbook, boring textbook. We're gonna just stick to this solid thing, okay? But make sure that there are other stuff, yeah? Small stuff and big stuff. Okay, so solid material is in one or two forms. Now we're gonna concentrate only solid, and they stay in crystalline state or amorphous state. Okay, so we call them amorphous materials or crystalline materials. Yeah. So let's go with the amorphous thing first. So amorphous materials. So these materials, they don't have repeating or three-dimensional geometric patterns. Okay, they're very chaotic. Amorphous mean like having no definite forms. They have a form and they're not definite. Okay, you can find the pattern in it. For example, glass. So when you see the structure of the glass, it looks like that, and they don't repeat. Okay, there's a whatever structure inside, but outside, oh my gosh, look at that! Whatever inside is very, very unique outside. Okay, everybody loves glass because you can have light through it, right, easily. So non-order structure, non-repeated pattern at the basic level of structure is going to give you beautiful outside, yeah, shining and beautiful outside that everybody wants. The next one is your crystalline. So crystalline solid, they have order, okay, they're ordered, they're repeated, and they're three-dimensional geometric patterns. There are 14 of them, but we're going to just take a look at 6. Okay, just a review. Nobody's going to ask you all about it. So we have simple cube. They're going to stay in that order. Okay, very, very definite structure right there. And repeated, of course. This is just giving you a unit. There are many of them, okay, built upon. And a face center cube, and a body center cube. And then we have simple tetragonal, okay, they're all geometrics. And this is body center tetragonal, and then we have the hexagonal close packed, okay? We use abbreviation, so if you see BCC, that's body centered cube. If you see like FCC, that's a face-centered cube. If you see like the hexagonal closed pack, that's an H, and then C, and then P. Okay, they're very, very common. Allotrophic is a material is going to exist more than one previously shown configuration, your unit cell. Okay, they may exist in more than one of these configurations, but under certain conditions, usually temperature stuff. So it means like materials can transform, okay, from one configuration to another, okay, one geometric form to another at different conditions. So some can transfer back to the original configuration, okay. There's a different natures that we discover, and we call that kind of nature allotrophic. So materials that can transform in both directions of configuration, we call them allotrophic, okay? So when you take a look at carbon steel, so this material is at BCC, so body center, yeah? At ambient temperature, mild temperature. In other words, goes to like 1400 degree Fahrenheit, okay? It changes its configuration to FCC, face center, okay? And then we bump the temperature 25,000 degree Fahrenheit. It's going to transform back to body centered. Okay? So why are they doing that? The basic fundamental thing is the change in condition, okay, transform the configuration, but the particles always try to find a way to stabilize, okay, back up. They always try to stabilize, okay, and sometimes we're going to end up with the original form, sometimes we're going to end up with a different new form, okay, when you change their form by setting a condition. That's just a big word. It's kind of like we already learned about the process of making structures. We strike them together, right? We attach them. The processes can be cutting, right? Attaching. Processes can be melting. Processes can be condensing, evaporating, or burning. Yeah, all kinds of stuff we do to shape the material into a particular structure. So if you burn the, let's say we'll take wood, everybody knows the wood, and go ahead, and that's a fiber, right? Molecular fiber, and you burn it. What did you get at the end? Always carbon, right? Ash. So that is what we're trying to show you. And when you take a look at, all right, the structure of the carbon ash and the structure of the wood, they're different. Okay. And now here is that we're particularly talking about the configuration of solid, okay, solid, and for allotrophic, okay, configuration, going with the unit cells, and show you how the configuration can change at different conditions, okay, and some of them can gain back the original configuration, yeah. And we call that in going both direction. Direction is not on the temperature, the direction is on the configuration. Okay, first go first direction and then go back to BCC. Okay, so you can take it out and you can go back, okay, and put this right here with different temperature. Yeah, and number it so you know the sequence. Okay, polymorph. Polymorph or polymorphid, we're just looking at the materials, and that materials can make transforming the configuration again in one direction only. Okay, then we call that polymorphid. There's no going back to the original configuration. So classification, you don't have to go into details. You only have to know industrial material classification system. Okay, and we're going to hit these things, and we will come back into that one by one in details in later chapters. So right now we're going to start right here at classifications. So we have this little table showing, okay, various industrial materials that we often use, and that's metals, and then we have polymers, ceramics, and then we have composites. Okay, metals, we're going to hit ferrous and non-ferrous. Ferrous is your iron and steel. Non-ferrous is magnesium, aluminum, copper, alloys, zinc. Noble metals, gold, silver. Not everything we're going to hit. Okay, some of them we're going to hit, some of them we won't. Synthetic, your plastic, adhesive, and elastomers. Your natural stuff is your wood, rubber, paper, and then ceramic. Now these two belongs to the polymers. Ceramics is going to be your flint and emery and clay, okay, garnet and diamond. We know this clay and diamond. We don't know this three, okay? We don't use that often, but we will study that. In ceramic, synthetic, we have aluminum oxide, silicon carbide, okay, and then zirconia, and then we have glass. We have cerulite, okay, then we have borosilicate. Now we get into the composite family. Now we're gonna hit polymer matrix, your fiberglass, your PEEK, your aramid epoxies, and then your plywood. Epoxy, everybody know, your car, okay, glue. Then your metal matrix, your graphite, aluminum, boron, aluminum, silicon carbide, and your titanium. And then we have your ceramic matrix, your concrete, okay, lithium, aluminum silicate, and the magnesium aluminum silicate, okay. And we're gonna hit all of that materials in later chapters. Okay, my throat hurts. I'm so glad it's finished. Okay, so this is it for Unit 2, okay.